All right, as we look to improve the Mark II wrist rockets for the new suit that we're building, it makes sense to kind of recap on the systems that make up that actual rocket launch. We have the containment, the ignition, the stabilization, and the sensing. But the ignition, that one can use a little bit more optimization. Looking at the previous build-up to where the igniter is now, it used to be just the basic off-the-shelf igniter you'd put in your model rocket. That works good enough to getting a basic test. We used it for the fin rockets, but it's not a durable igniter. It breaks a lot of the time. It's very fragile, especially if you have a rocket that's spinning super fast. If you have your igniter on the inside, not really the best solution going forward, especially for like a full Iron Man suit. Those are also not repeatable. They're one-use igniters. Every time you use it, you have to swap it out, put a new one in. The next version I tried was an arc lighter, putting the leads of an arc lighter in the back of the rocket. Works a little bit better for the spinning. I got one successful test off of that. Also looking at the repeatability of that system, what happens is the leads that you put in the back of the rocket, they get completely melted. So what I've settled on now and have done most of my tests with recently has been with the laser igniter. The laser igniter is great because it can stay a certain distance away from the actual rocket itself. It doesn't have to be actually embedded in the back. We use the focal point of the beam and place it at the point of ignition on the inside of the rocket. That's really reliable in terms of generating the heat quickly and fast enough to actually ignite the rocket in like a reasonable manner. With that in mind, there's a lot of power requirements for a laser that allow it to actually perform that way. If I use like an off-the-shelf laser pointer from like a Home Depot, that one's not gonna heat up in any sort of meaningful way. I originally used a 4-watt green laser, a little bit lower power. That one worked for a couple of tests, but it still wasn't consistent. Then now I'm using a 7-watt blue laser, a lot more power output, a lot more consistent, and actually is what we use for the most recent tests as well. Clearly it works in principle, but there's a couple of paths of optimization that we can use to better improve the system. Right now the ignition system is not as seamlessly integrated into the actual rocket subsystem as like all the other ones are. The rocket flap had like an integrated motor driver that used like flex cables to connect everything, and it was kind of folded on itself to fit nicely in there. The laser driver that I use now is just kind of exposed on the outside, kind of hanging off wires. The current driver that I use now works great. It's a 4.5 amp output. That works great for the laser. We get the kind of power that we want. But if we want quicker ignition, we can probably get a little bit more power out of the laser that we use now. So I'm looking to do about 5 amp output on the laser. When it comes to driving a laser diode or like a LED, they kind of fall in the same realm in terms of electrical control. There's a parameter that diodes have called the forward voltage. That is the voltage drop that is needed across a diode in order for it to actually start conducting electricity. So a lot of the times with an LED, you'll see like a resistor paired in series with your LED. That resistor has a certain voltage drop across it that allows the actual voltage drop across the LED to match the forward voltage. And that is all to provide what is called your forward current, which is the current that runs through the diode at that forward voltage. Forward current is kind of the most important part. As LEDs and laser diodes operate, they heat up. That changes the LED's forward voltage, and that makes it want to draw more current. And as it draws more current, it heats up, and then it changes the forward voltage even more. So it's kind of like a negative feedback loop that happens. So having a very stable current output that kind of matches the forward current is what you need for stable diode operation. We need to somehow now regulate 5 amps across our laser without it being unstable, kind of changing with voltages. They're very sensitive to current spikes and a bunch of different weird current behaviors, so we need a very stable current output for the time that the laser's on, and we need a very quick turn on and a very quick turn off for our laser operation. So if we look at the actual architecture of the current laser driver that we have now, you can kind of get an understanding of the operation. It has a bunch of extra features, which is why you might see like an inductor and a bunch of other stuff, but there's clearly an op amp and there's clearly a MOSFET on there. An op amp is an operational amplifier. It takes an input and it amplifies the output. That's the basic functionality. However, it has a positive input and a negative input, and as you compare the two, what it does is it adjusts that output to see if it can get that negative input to match the positive input, at least in the non-inverting configuration, which is what we're doing. That uses a reference voltage on the input. The output is boosted through some sort of gain factor, and that's kind of a standard term in controls. That gain multiplies the input to create an output. That output is then used to power something. The output would ideally be used to drive the laser directly. You know, you just have whatever voltage across the laser to draw the amount of current that you want. Boom, your laser is being controlled. However, 5 amps through the actual little op amp that we're using is way too much current for the little guy to handle. So we're not going to be able to drive it directly from the op amp. However, a MOSFET is a perfect solution for high current draw. You can think of a MOSFET, a metal oxide semiconductor field effect transistor. You can think of that as basically just an electrical switch. But at its core, the MOSFET is actually a voltage to current converter. If you really think about it, what's happening is that you set a voltage at the gate, and that voltage then gets converted into a proportional current output based on what's called the transconductance parameter. And that's essentially like a multiplication factor. So we need a way to create a gate voltage that corresponds to our actual 5 amps of current through the MOSFET. So what we can do is we can take the MOSFET and connect the gate to the actual output of the op amp, because what the op amp does is it creates an amplified voltage from our reference input, which we can then use to create our gate voltage, which then creates the proportional relationship to the drain current, which is what flows through the laser. So now we have a framework to actually allow high current to flow through our system. What we need to do is find a way to gather information about the current flowing through our laser and feed that back to the op amp so that it knows how to adjust the output to then adjust the MOSFET to then adjust the current flowing through our laser. So to do that, a lot of sensing electronics use what's called a sense resistor, which is essentially a very small resistor. The value is like tiny. And in our case, I selected a 10 milliohm resistor, which is a tiny value, but at 5 amps, what happens is that you have a voltage drop of 50 millivolts, which is not an insignificant voltage. So then we can actually use the op amp to observe that voltage and adjust the output based on the actual observed voltage and the desired voltage, because the op amp itself can't necessarily read current. So what we do is we put that sense resistor in series with our high current flow, and that reference voltage we automatically set to 50 millivolts, so we tell the op amp how it should adjust the output based on that differential. So what we're doing is we're reading the actual voltage across the sense resistor with our negative reference and comparing it to our 50 millivolts, because if 50 millivolts isn't actually detected at the sense resistor, that means that we don't have 5 amps flowing through our laser. However, that comparison creates a response of the op amp, and that's what sets the output. So the amplification inside the op amp has a very high internal open loop gain. What it does is it aggressively tries to pump up the output based on the difference between the positive and negative reference, and that could lead to overshoot, which could then damage the laser. So now that we have this feedback loop taking the sense resistor voltage, what we need to do is kind of tame that control loop in a way that's not super aggressive. So what you can add is a capacitor and resistor that both have implications on how the actual control loop behaves. But if we look at the capacitor specifically, the main thing there is that it adjusts more of the damping factor. That lowers the kind of rate that the signal wants to rise, which then correlates to how aggressively our current rises. And the resistor itself affects a lot more of the aggressiveness of that response. So as we adjust the resistance value, we tune how aggressive that response is going to be. Coupled with the capacitance, you can kind of smooth out the aggressiveness and response of that control loop. And using a simulation software like LT-Spice, we can actually simulate the current response and tune those two values to find out where they should be. So that's what I use a lot to actually find out how we should design this specific circuit and not necessarily go in too blind. You can imagine translating a simulated circuit from LT-Spice to an actual PCB may have slightly different behaviors. We need to have a little bit more extra safeguards to protect our laser from current spikes. And that manifests in the way of what's called a soft start. And the soft start itself also uses a resistor and a capacitor. So in this case, the resistor and capacitor create what's called a time constant. The multiplication of the two values creates a time constant. And that time constant actually dictates the rate of increase for the current. So instead of immediately setting it to 50 millivolts, what happens is that you have to have the capacitor actually charge up first before reaching 50 millivolts on the reference, because the op amp observes the actual capacitance voltage. So instead of immediately seeing 50 millivolts, what you see is the voltage of the capacitor as it charges, and that gradually increases to 50 millivolts, and that gradually increases the output of the op amp, which gradually increases the current to an extent that it lowers the risk of overshoot, but not too slow that it's going to affect the actual operation time. And that's another feature that we can tune in our simulation by just looking at how the current response is at the beginning and just making sure that we don't see overshoot as well. So now we kind of have an idea of what the circuit should look like for the actual laser driver, but we need to make sure that we eliminate most of the risk for an actual overshoot on the laser. So after iterating on the simulation and adjusting the schematic to get a proper current response, I then needed to actually test the circuit in real life and make sure that my simulation kind of matches reality. So in order to do that, I needed to get a custom PCB made to actually prototype the circuit and test the response in real life. So for that, I use PCBWay, which is a great service that has a lot of capabilities, and we'll talk about them later. So now prototyping our circuit on the PCB, the very first attempt, which correlated to our kind of first initial simulation response, that one was not working well. It had a super high current draw, overheated extremely quickly, but I designed the PCB in a way that I could actually test different parameters and simulation configurations. So then I continued to iterate on the simulation and get a much better response, and that is what I have now, which seems to be working a lot better. So thanks to PCBWay for helping out with that. If you want to check them out, the link is in the description. There's a lot of services they offer. They have PCB manufacturing, they have 3D printing, sheet metal cutting, a lot of things you can do, a lot of services you might need if you want to build your own products as well. And PCBWay is super simple to use. All you have to do is just export the Gerber file from whatever design software you're using to make your circuit. Go to PCBWay, go to their website. They have a very easy interface to actually order the board itself. All you got to do is just kind of configure your board. You can set your dimensions, you can set how many boards you want, you can set board thickness, how many layers, all the important parameters for a PCB. And then all you have to do then is just import your Gerber file. They'll get back to you on kind of how their design is going to come out, maybe if you need to make any changes. Very informative. And then you can order the PCBs and it'll arrive at your door a couple days later. Nothing crazy. And here you can see the actual PCB from PCBWay. Came out just like the designs I made. Everything looks great, so we can actually now do our circuit prototyping on there and maybe see if we can get a better performance than the original driver. So I was able to still use that same PCB, adjust the circuit in a way that's a lot better in terms of how the actual current loop is structured. And then I was seeing a much better response. I was able to see my input from my reference voltage correlate to an actual output on the laser. However, the actual amplification of that value wasn't exactly what I wanted. My 50 millivolt input wasn't directly correlating to 5 amps on the output, but for my green laser, my blue laser, I wasn't seeing current spikes or any crazy behavior on the output. So it seems like the actual base behavior is there. It doesn't look like anything crazy is happening, but the actual amplification and the sensing from the sense resistor seems to be a little off. And from what I found, I was able to actually crank up the reference voltage and see the actual output current also go up. What it means is that my sensing circuit is probably not working well. There's an integration technique called Kelvin sensing that I tried to do, but I think I didn't do perfectly. And essentially what it does is it creates a dedicated path for your actual high current flow and your sensing current. What you do is you take a little offshoot of the sense resistor and feed that back into whatever your sensing mechanism is, which for us would be the op amp, And that is a much better and more refined way to actually accurately read that sense resistor voltage. I think I did it a little wrong by not having a dedicated ground path for the actual resistor, so the voltage drop is probably getting corrupted a bit and affecting how the actual output behaves. That should be a quick and easy fix for the next version. Seems like things are working pretty good for this driver, but now that we kind of have the basic understanding of the current loop working, should be a pretty easy project to finish up. The rockets are the main focus right now, so keeping our heads down for that, locking in, focusing. But next we might look at the flamethrower again because that's a pretty solid one. So stay tuned for that, and thanks to PCBWay for sponsoring this project.